In this video, we consider finding the domains of compositions of functions. That is, functions of the form h of x equal f of g of x, where the f of x and g of x are simpler functions. As a first example, let's look at h of x equal the square root of 3x minus 5. If we're going to think of this as being an h of x equal f of g of x, then the outside function f of x, the last thing we're doing is taking the square root. And the inside function g of x, the first thing we do is compute 3x minus 5. So let's start by finding the domains of each of these simpler functions f and g. The domain of f is all x greater than or equal to 0. The domain of g is all real numbers. I'll use the all real number symbol there. But that doesn't mean that for the function h, we need all x's greater than or equal to 0. For h, we have to make sure that the thing that we're taking square root of is greater than or equal to 0. In other words, our x's first have to be able to go into g. That's fine. All real numbers work there. But then the numbers that come out of g have to be able to go into f. And so the numbers coming out of g, the 3x minus 5 numbers, have to satisfy the domain of f. They have to be greater than or equal to 0. So this gives us an algebra problem to solve. This is a simple algebra problem. We can add 5 to each side, divide by 3, and we get that x is greater than or equal to 5/3. And then we have to consider all of the x's that meet both of these conditions. They can be fed into g in the first place, and that means in the domain of g, but then the outputs of g fit into the domain of f, and that was our condition x greater than or equal to 5/3. So we take the intersection of these two, that just means all the x's that satisfy both of them, and all the x's that can be anything and also greater than or equal to 5/3 leads us to the domain of h being, and I'll put this in interval notation, the interval from 5/3 to infinity. And just to remind you, the bracket means include the 5/3. If we weren't including the 5/3, we'd put a parenthesis. So let's try this process on our second h of x. This time we have the square root of x plus 1 over x minus 3. Again, I want to be thinking of this as some outside function applied to some inside function. So our outside function is again the square root of x. This time our inside function is the rational function x plus 1 over x minus 3. The domain of f is again x greater than or equal to 0. The domain of g, this rational function, will be defined for all real numbers except 3 because we can't divide by 0. So this will be one of our conditions we have to keep in mind. Our x's first of all go into the inside function, so they have to be in the domain of g. But then we have to make sure that that which is coming out of g, so right here for h, the condition that we have to have satisfied is that x plus 1 over x minus 3, the output from g, has to be a legal input for f. Has to be greater than or equal to 0. And so again, we have an algebra problem to solve. This one's a little bit harder. Hopefully you've dealt with these in Algebra 2 or Pre-Cal or both. The easiest way to solve is to go to the number line, mark on it any zeros of the numerator or the denominator. We want to include the case where we get 0. That happens when the numerator is 0 at -1. And of course we have to exclude the case where the denominator is 0, and so I'll put an open circle on the 3. That's actually an outgrowth of our domain of g. And then our process is to look at each of the 3 resulting intervals and decide whether x plus 1 over x minus 3 is positive or negative, and the result of that investigation is a plus minus plus. We look back at our inequality. We want this quantity to be greater than or equal to 0, so I choose the intervals where I have the plus sign, and I put this condition together with the domain of g, and take the intersection of those two, and we find that the domain of h in this case is the interval from negative infinity to 1, bracket, together with, I'll write union, parenthesis 3 to infinity. And so let's box in our answers so that it's clear from our work what our final results for the domain of h are. Okay, let's look at one more example. H of x is 1 over ln of x minus 3. And this time, if we're looking at this as an f of g of x, then our outside function, f of x, is the reciprocal function, 1 over x, and our g of x function is the function ln of x minus 3, that thing that we're taking the reciprocal of. Domain of f is all real numbers except 0. Domain of g, if you remember what the ln of x graph looks like, looks sort of like this, hits the x-axis at 1, asymptotic to the y-axis, and we can read off from that that the domain of this ln of x function, and hence of ln of x minus 3, is x greater than 0. But that doesn't mean that our final answer for the domain of h is x greater than 0. What we have to assure ourselves of is that these numbers coming out of g, the ln of x minus 3 numbers, satisfy the domain of f, are not equal to 0. And we have an inequality to solve here for x. This says that ln of x cannot be 3. And if we change this into exponential form, that says x cannot be e cubed. So our two conditions that our x's have to satisfy, they first of all have to be able to go into g, so they have to be greater than 0, and they have to leave us with a result that lets the ln of x minus 3 is not equal to 0, in other words, not equal to e cubed. Putting these together, our answer for the domain of h is the open interval from 0 to e cubed, not including the e cubed, together with the open interval from e cubed to infinity. And that's a process that can help us think our way through finding the domain of the composition of functions.